have epic, filled with giant machines, fire, and incredible force. The Acme Brick Company's factory in Denton, Texas, produces approximately 130 million bricks a year. 130 million. Let's try to wrap our heads around that. That's over 350,000 bricks every single day. That's almost 15,000 bricks every hour. This means that every minute, 24 hours a day, 7 days a week, over 240 finished, clinking bricks roll out of its kilns. While you listen to one song, this factory produces enough bricks to build a small wall. And in a year, that's enough to build over 6,000 average American homes. Imagine a whole small town built from the bricks produced at a single... This is a journey from dirty earth to perfectly stacked piles, ready to become part of a skyscraper. It all begins not at the factory, but in a huge pit called a quarry. This isn't just mud under your feet. It's a special clay or shale rock that has been waiting for its time for millions of years. A giant excavator, with its massive bucket capable of lifting a car at once, bites into the earth. It rips out tons of this rock and with a roar, dumps it into the bed of a dump truck the size of a small house. These monster trucks haul mountains of raw material and pile it up on the factory yard, where it can lie for weeks or even months. This isn't laziness. It's the first stage of processing weathering. Rain, sun, and wind begin their work, making the clay more plastic and pliable. Then back for regrinding. The goal is to get a perfectly fine, uniform powder. Now this powder, resembling dust, is ready to become dough. It is fed into a giant mixer, where a precisely measured amount of water is added. Dry. Its consistency is controlled with computer-like precision. The next stage is perhaps the most incredible sight in the entire factory. This is extrusion. The clay dough is fed into a machine called an extruder. Essentially, it's like a giant meat grinder or a pasta-making machine. A huge screw, or auger, pushes the clay mass, compressing it tightly and removing the last air bubbles. This is very important because any air bubble can shatter the brick during firing. At the end of the extruder is a special nozzle, or die, shaped like a perfect rectangle. Robotic arms, with incredible speed and precision unattainable by humans, grab the hot bricks and stack them into perfectly even cubes for packaging. They don't get tired, they don't make mistakes, and they work at a frantic pace. But first, let's get back to the story of the fresh brick. Now, imagine a giant sauna several hundred feet long. Inside these chambers, a specific temperature, from 100 to 400 degrees Fahrenheit, and a very precise humidity level are maintained. Hot air circulates around each brick, slowly drawing moisture out of it. This process can take from 24 to 48 hours. During this time, the brick loses a significant amount of its weight, becomes lighter in color, and much harder. Now you can hold it in your hands, but it still doesn't have that legendary strength. And now comes the culmination, the trial by fire. The dried brick is ready for firing. The kiln cars with neatly arranged bricks enter a tunnel kiln. This is a true monster, a structure 500 feet long, the real heart of the factory. Inside this kiln, the brick will make its hottest journey. It slowly, at a turtle's pace, moves through different temperature zones. First, it enters a preheating zone, where its temperature gradually rises. Then, it enters the central firing zone, into the very inferno. Here, the temperature reaches 2,000 degrees Fahrenheit. The chemical miracle called vitrification occurs. The clay particles begin to melt and sinter together, forming a strong, glass-like structure. It is at this moment that the brick acquires its final color, which depends on the mineral composition of the clay and the firing temperature, and its incredible strength. But exiting the kiln is just as important as entering. The last third of the way, the brick passes through a controlled cooling zone. Its temperature is just as gradually lowered. Too rapid cooling will lead to thermal shock, and the brick will simply crack. When the kiln car finally emerges from the other end of the tunnel, it carries finished bricks. They are hard as stone. Robotic arms, resembling giant claws, remove the bricks from the kiln cars and stack them into perfectly even cubes. Usually, there are 500 bricks in one such cube. Then, an automatic packaging machine wraps these cubes with strong metal or plastic straps and wraps them in branded film to protect them from rain. The final stage is logistics. Yellow forklifts, deftly maneuvering through the huge warehouse, pick up these heavy cubes and load. To transport all this production, a whole fleet of trucks is needed. Considering that one truck on average is loaded with about 10,000 bricks, then every year, 13,000 fully loaded trucks leave the gates of this factory. That's over 50 trucks a day, including weekends. This is a continuous stream of transport, delivering these small red rectangles throughout the region. So, the Acme Brick Factory in Denton is not just a place where bricks are made. It's a vivid example of how modern technologies, robotics, and incredible scales transform ordinary clay into one of the most important building materials that shapes the face of cities and suburbs in America. Now, the next time you see an ordinary brick wall, you'll know that each of these small rectangles is a veteran that has gone through crushing, mixing, forming, multi-day drying, and an infernal fire to become a reliable and durable building block of our world. Every year in the United States, about 27 billion square feet of drywall are produced. That's enough to lay a continuous path from the Earth to the Moon, and still have enough left for the way back. Imagine millions of tons of stone torn from the depths of the earth, passing through giant crushers, furnaces, and conveyors to become the smooth walls of our homes. But the real magic of this process begins where ordinary gray stone becomes a thirsty powder and gains the ability to become stone again. Watch until the end, and you'll learn the secret that makes this possible. The numbers behind drywall production in the United States are not just big, they're astronomical, and they tell a story of how the country builds, renovates, and breathes. In a recent year, factories in the United States produced approximately 27 billion square feet of drywall panels. This number is so colossal that it's hard to comprehend. Try to imagine, if you laid out all this drywall, you could create a continuous 3-foot wide path that would stretch from the Earth to the Moon and almost halfway back. Or you could completely cover the entire territory of the state of Delaware twice with this amount of sheets, and still have some left over. This endless stream of building material is not just a physical product, but a powerful economic indicator. The market for these panels in the United States is valued in the tens of billions of dollars, reflecting not just the cost of the material itself, but also thousands of jobs in mines and factories, in logistics and construction. It all begins not in the workshop, but much earlier, in the quarry where gypsum is mined. This is a natural mineral, a stone that formed millions of years ago from ancient seas. It can be white, grayish, sometimes with pink veins. Huge excavators dig into the gypsum deposits and load dump trucks with boulders of this stone. These trucks bring tons of gypsum to the factory and dump it onto the raw material yard, creating entire mountains waiting for their transformation. The first stage inside the factory is coarse crushing. The gypsum boulders fall into the giant steel jaws of the primary crusher. With a deafening roar and grinding, the machine breaks the large stones into smaller pieces, about the size of a fist. This is just the beginning. Then, this crushed gypsum is fed by a conveyor belt to secondary mills. Here, dozens of steel hammers, spinning at insane speeds, break these pieces into even smaller fractions, turning them into something like coarse gravel. But even this is not enough. The final stage of grinding turns the gypsum into a fine powder, like talcum. It becomes so fine that it resembles flour or dust. This powder is the main raw material, but it still hides a secret that needs to be unlocked. The next step is one of the most important and interesting. This is a process called calcination, and in essence, it's the controlled drying of gypsum. The thing is, molecules of water are locked within the crystal structure of natural gypsum. To allow the drywall to harden, this water must be temporarily driven out. For this, the white powder is fed into a huge, slowly rotating furnace. It looks like a giant drum, tilted at a slight angle. Inside this furnace, a very precise temperature of about 300 degrees Fahrenheit is maintained. The gypsum powder, slowly tumbling inside the drum, heats up, and the water bound to it turns into steam and evaporates. Chemically speaking, gypsum turns into calcium sulfate hemihydrate, but in simpler terms, it becomes thirsty. Now this powder, which is already called building gypsum or stucco, has a unique property. If you add water to it again, it will greedily absorb it and turn back into a solid gypsum stone. It is this property that is the basis of the entire production. The resulting hot powder is cooled and stored in giant silos, resembling towers, from where it will be fed to the main production line. And now the most spectacular part begins, the creation of the sheet itself. In the workshop is a huge, hundreds of meters long conveyor. At its beginning stand two giant rolls of special dense paper, cardboard. One roll for the face side, it's perfectly smooth, white. The other for the back side, it can be a bit darker, grayish. The tape from the bottom roll, the face side, unwinds and lies on the conveyor, forming an endless track. Simultaneously, in a giant mixer, similar to an industrial food processor, the core is prepared. Our thirsty gypsum powder, water, and a whole cocktail of various additives are continuously fed into it. Each additive plays its role. Foaming agents make the gypsum mass lighter and more porous, like whipped cream, to reduce the weight of the sheet. Plasticizers make the mixture more fluid so that it spreads evenly. Accelerators or retarders allow engineers to perfectly control the time it takes for the gypsum to set. Starch helps the gypsum core to better stick to the paper shell. Fiberglass adds strength. This mixture, called slurry, resembles a thick gray paste. It is poured in a continuous stream directly onto the paper tape moving along the conveyor. Special devices evenly distribute this mass across the entire width of the paper. The edges of the bottom sheet of paper are neatly folded upwards, forming the sides of the future sheet. And at this moment, it is covered from above with a second tape of paper, from the back roll, like a lid. The result is an endless, perfectly even sandwich. Paper, gypsum mass, paper. This sandwich immediately passes between two rollers, or under a forming plate, which compress it to a precisely specified thickness, for example, ½ inch. Just formed, still soft and wet, the drywall sheet continues its journey on a very long conveyor, called the setting line. Its length can reach several hundred meters. While the sheet slowly moves, a real miracle happens inside it. The gypsum powder reacts with water, the same rehydration reaction occurs. The gypsum turns back into a solid stone, releasing heat in the process. If you touch the sheet at this stage, it will be warm. In a few minutes, the loose mass becomes hard enough to hold its shape. At the end of this long line stands a flying knife. This is a huge blade that moves in sync with the belt and, at the right moment, makes a quick, precise cut, slicing the endless sandwich into sheets of standard length, for example, 8 or 12 feet. This happens so quickly that the conveyor does not stop for a second. The cut sheets are now solid, but still very wet. They contain excess water that did not participate in the chemical reaction. It needs to be removed. Therefore, a special device flips the sheets and feeds them into the most large-scale structure in the factory, a multi-story drying chamber. This is a giant labyrinth consisting of several levels, each of which is a conveyor. The drywall sheets slowly move along these levels back and forth, covering a path of several hundred meters inside this huge furnace. Hot air circulating inside gently evaporates the excess moisture from them. The temperature here is controlled very carefully. It is necessary to remove only the free water, without damaging the crystal structure of the gypsum itself. This process can last about an hour. At the exit of the dryer appears our familiar product, a perfectly dry, light and durable sheet of drywall. But this is not the end yet. The final stage is finishing. 2 finished sheets are stacked face sides together. Their edges are perfectly trimmed to be even and clean. A paper tape with information about the manufacturer and product type is glued to the end. After this, robotic manipulators with inhuman precision and grace lift the finished sheets and stack them in perfectly even stacks on pallets. Each stack is wrapped in protective film, marked and sent to the warehouse. From there, it will go to construction sites to become part of someone's home, having transformed from a simple grey stone mined from under the ground into a smooth and cozy wall. The production of drywall is like a barometer of the health of the construction industry. When the economy is on the rise, people are actively building new houses and renovating old ones, and the demand for drywall sharply increases. The factories that produce this product work at full capacity, and the stream of trucks delivering finished sheets throughout the country becomes endless. The heart of this production beats in unison with the rhythm of the real estate market. Geographically, this industry also has its centers. Although drywall factories are located throughout the country, to be closer to large construction markets, the mining of the main raw material, gypsum, is concentrated in certain states. The leaders here are states like Texas, Oklahoma, Kansas, Nevada, and Iowa. Every year, over 2 billion tons of steel are produced worldwide, but only a fraction of it becomes I-beams, the backbone of skyscrapers and bridges. These factories are entire cities with smokestacks as tall as a 30-story building and cranes that can lift a railcar along with its locomotive. For one beam to be born, ore goes through over 2,700 degrees Fahrenheit in a blast furnace, a dozen rolling stands. A modern rolling mill produces a new beam every 30 seconds, like a car assembly line, only each car weighs 3 tons. Why does the H shape save tons of metal and protect buildings from collapse? I'll show you with a simple example. Watch until the end. One invisible flaw of 1 millimeter, and you'll see what breaks even perfect steel. The entire process begins not in the workshop, but deep in the earth, where iron ore is mined. This ore is transported to metallurgical plants, true industrial cities, with smokestacks as tall as a 30-story building. Here, the ore is mixed with coal and melted in blast furnaces at a temperature of over 2,700 degrees Fahrenheit. Such a temperature can melt copper coins in a matter of seconds. As a result, liquid iron is obtained, which is then purified of impurities and turned into steel. Steel is not just iron. It's an alloy to which a precisely calculated amount of carbon and other elements are added. Even 0.1% can drastically change the metal's properties. Too little carbon, and the steel will be as soft as clay. Too much, and it will be as brittle as glass. Therefore, steelworkers operate with the precision of pharmacists, controlling the composition of the melt using computer systems. When the steel is ready, it is poured into huge ladles and transported to the next stage. Here, the molten metal is poured into special molds, resulting in blanks called billets. These billets resemble huge metal bricks weighing up to several tons each. They do not yet look like beams. They are just rectangular bars of hot steel that glow red in the dark. The real magic of transforming billets into I-beams happens on the rolling mills. The steel blanks are heated to high temperatures and then passed through a series of rollers to give them the desired shape, including I-beams. These mills are true monsters of heavy industry. Imagine a machine the size of a trolley bus, consisting of dozens of rollers with a diameter of more than 1 meter. Each roller weighs as much as an average car and spins at the speed of a bicycle wheel. Gradually give it the desired beam shape. The rollers exert enormous pressure, giving the beam structural strength. The process resembles rolling out dough, only instead of flour, there's a multi-ton steel blank, and instead of a rolling pin, there are rollers that could flatten a car in a second. In modern steel rolling, I-beams are rolled on universal rolling mills. The web of the I-beam is rolled between the... This is like a complex choreography, where dozens of rollers move in sync, gradually transforming the rectangular blank into the elegant shape of an I-beam. Temperature here is critically important. Hot rolling involves passing heated steel through rollers, shaping it while maintaining a plastic working temperature. If the steel is too hot, it might deform incorrectly. If it's too cold, it could crack under the pressure of the rollers. The temperature is controlled by pyrometers, devices that measure heat from a distance, like sniper thermometers. Interestingly, the I-beam shape is not a designer's whim, but the result of precise engineering calculations. Such a design allows for maximum strength with minimum metal weight. Imagine a bridge. The main loads are on the top and bottom of the beam, which is why the wide flanges of the I-beam are located there. And in the middle, where the stress is less, a thin web is sufficient. The rolling process takes several minutes for each beam, but during this time, it passes through 12 or 15 pairs of rollers. Each pair has its own shape, gradually bringing the blank closer to the final profile. It's like sculpture. First rough forms, then more and more details and precision. When the beam emerges from the last pair of rollers, it's still glowing hot, 1,650 degrees Fahrenheit. In the air, it glows with an orange light and can ignite wood on contact. Therefore, the beams are cooled on special racks, where they gradually darken, acquiring the characteristic grayish-blue hue of hot-rolled metal. Hot rolling shapes metal beams at elevated temperatures, making the material more ductile. As a result, this method supports the production of large sections and complex shapes. That is why most structural beams are made by hot rolling. It allows for creating powerful structures for skyscrapers and bridges. But the process doesn't end here. The cooled beams undergo quality control. They are inspected with ultrasound, like conducting an ultrasound on a pregnant woman, only instead of a baby, they are looking for internal cracks in the metal. The dimensional accuracy is also measured with special templates. Even a millimeter deviation can ruin the entire structure of a building. After the red-hot metal has passed through the giant rollers of the rolling mill and been transformed into the recognizable H-shaped profile, the I-beam enters one of the loudest and most spectacular stages of its birth, marking and cutting. Freshly formed, still glowing red or bright orange, the beam slowly moves along a roller table, a long conveyor of rollers. Along this path, the color of the metal fades, turning to a dark cherry red, and then to the familiar gray. This process, known as normalization, relieves internal stresses in the metal that arose during rolling, and gives the beam the necessary strength and ductility. Resembling a giant industrial printer, applies a clear and durable imprint on the beam's surface. This is not just a random set of symbols. The marking contains all the key information about the beam, with guaranteed characteristics, ready for use in the most responsible projects. the most spectacular and deafening stage is cutting. Long beams, sometimes over 300 feet, are fed to the cutting complex. The heart of this complex is giant pendulum or circular saws. Imagine a circular saw, sharp carbide teeth. Controlling the process from a protected cabin sets the required length. Powerful hydraulic clamps fix the beam. Preventing it is the speed of the whole process. From the moment the iron ore arrives at the plant to the finished beam takes less than a week. During this time, the metal has time to melt, be purified, solidify, be heated again, and be transformed into a precise structure. A modern rolling mill can produce a beam every 30 seconds. It's like a car assembly line, only each car weighs 3 tons. The finished beams are loaded onto trains by special cranes. Such a crane can lift a rail car along with a locomotive. The beams are transported to construction sites all over the world, where they will become the skeletons of skyscrapers, factories, shopping malls, and bridges. Each such beam is the result of the work of hundreds of people of various professions. Miners who extracted the ore, metallurgists who smelted the steel, rolling mill operators, quality controllers, and crane operators. This is a true industrial art, where the precision of a pharmacist is combined with the power of a volcano. And when you see a new skyscraper or bridge, remember, at the foundation of our civilization. Every year, only a few dozen combat machines capable of changing the course of a battle are produced worldwide. One such giant is born in the heart of the United States at the Boeing factory in Fort Worth, where every bolt, every weld seam is inspected with micron precision. Here, fuselages made from metal plates are joined into a single, strong body, and powerful T-700 engines and Hellfire missiles turn the machine into a formidable weapon. But there is one detail that only those who work behind the scenes of this production know. Watch until the end, and you will discover a secret that changes the perception of these helicopters forever. The main production facilities are located in the United States, particularly at the Boeing plants in Fort Worth, Texas, where the helicopter is manufactured using modern technologies. At these plants, the assembly of the helicopter's main components, such as the fuselage, rotors, and weapon systems, takes place. The production process includes automation to increase efficiency and accuracy, which is critically important for military equipment. An important part of the production capacity is also contracts with component suppliers. Orders for electronics, engines, control systems, and other parts come from various corners of the world. These suppliers must meet strict quality standards to ensure the reliability and combat readiness of the helicopter. In addition, the U.S. Department of Defense works closely with Boeing to control production, which allows for ensuring compliance with all specifications. This includes conducting regular inspections and tests at various stages of production to account for all potential problems. The production facilities engaged in the manufacturing of the AH-64 are also constantly improving their processes. With the introduction of new technologies and production management methods, such as lean manufacturing, the company strives to reduce costs and shorten production time without compromising quality. The main components, such as electronics, engines, navigation, and control systems, are manufactured in different countries. For example, the T-700 engines used in the AH-64 are produced by General Electric in the USA. Weapon systems, such as Hellfire missile launchers, are manufactured by many defense contractors, both in the US and outside the country. The electronic system, including radar and fire control systems, is supplied from various countries, such as Israel and the United Kingdom. This allows for the integration of innovative technologies that are constantly being improved in military aviation. The delivery of components to the Boeing production facilities in Fort Worth is carried out through various logistics channels. International transport is often carried out by air and sea, depending on the urgency and volume of the cargo. Key components can be delivered by express air transport to reduce manufacturing times. Upon arrival at the Boeing plants, the components undergo additional inspection to identify possible defects and non-conformities. After the delivery of all components to the Boeing production facilities, they arrive at the huge factory territory in Fort Worth, where several hangars are organized for helicopter assembly. Here, a primary inspection of each batch of parts is carried out. Specialists carefully inspect the components to identify any defects or non-conformities with standards, which ensures a high level of quality. The production process begins with the assembly of the fuselage, which is the helicopter's foundation. In this stage of work, huge metal panels, drawn out in the form of long and wide sheets, are used. The fuselage consists of several sections that are welded together to create a single, strong body. First, the workers coordinate all requirements and drawings, focusing on the accuracy of measurements. They carefully install the fuselage base on a special platform that allows easy access to all elements. In parallel with this, engineers ensure that each element meets strict quality standards. During the fuselage assembly process, workers use a variety of tools, from electric drills to specialized welding machines. Welding takes place far from any unpredictable movements, as this is critically important. Even the slightest inaccuracy can affect the helicopter's combat stability. The flame of the welding illuminates the workspace, adding a bit of heat to the surrounding environment. After the main parts of the fuselage are joined, it is checked for leaks. This includes leak testing liquid is pumped through special pipes to ensure that the body's reliability meets the requirements. Usually, workers suspect a problem if they hear a sound similar to a whistle or a pop, which could indicate issues. When the fuselage successfully passes all tests, it is time for painting. The application of coatings is important as it prevents corrosion and increases resistance to weather conditions. After painting, the fuselage is sanded to ensure a smooth surface, and then all parts are checked again to confirm they are installed correctly. After the fuselage assembly is complete, the next stage is the installation of the electronic systems, which play a critical role in the combat effectiveness of the AH-64. After the fuselage is prepared, it is moved to a special hangar where technicians begin to carefully install various electronic components. These systems control everything from navigation to the weapon control system. During this process, specialists install elements such as radar, which provide an overview of the battlefield, as well as fire control systems. These components are particularly sensitive, so it is important to adhere to huge accuracy. Workers use various tools, such as drills and screwdrivers, as well as specialized devices for laying wires. The next step is the installation of the engines. For the AH-64, T700 engines are used, which are powerful and reliable. After the engines are delivered to the factory, technicians check them for compliance with technical specifications. During the installation process, the engines are mounted on the fuselage, and all necessary systems, such as fuel supply and cooling, are connected. This process requires great attention to detail, as the engines must be securely fixed and correctly connected. After the installation of the engines and electronics, the stage of integrating the weapon systems begins. The helicopter is equipped with various armaments, such as Hellfire missiles and an M230 machine gun. In this stage, technicians use multi-step procedures to install and calibrate the systems. Each weapon unit is equipped with electronic systems that ensure its functionality. After installation, a check for the compatibility of all components is carried out. Having completed the integration stages, the fuselage proceeds to final assembly, where various systems are connected hydraulics, as well as control mechanisms. Hydraulics provide the helicopter's mobility, and its installation is a critically important task. Technicians check all connections for tightness, as a leak of hydraulic fluid can lead to serious problems during flight. During the testing of the AH-64, a real show of technical skill takes place. Aerodynamic checks are conducted in a large open area where the helicopter takes to the air, demonstrating breathtaking maneuvers. From a height, it performs turns, hovers in the air, and makes steep descents, showing its stability and ability to react quickly to the pilot's commands. Spectators can see how the powerful engines work at maximum revs, filling the air with their roar. On the ground stand, the atmosphere is also tense. Experts closely watch every movement of the helicopter, keeping an eye on the digital indicators on the monitors. The sounds of testing the electronic system, as the helicopter actively responds to control commands, are impressively complex. When the weapon system is launched and green indicators appear on the monitors, everyone present experiences a moment of elation. It's a sign that everything is working, and the helicopter is ready for combat missions. The team of engineers is gathered on the territory. They are dressed in special equipment and focused on their work. When the entire system passes the checks, a look of satisfaction appears on the experts' faces. Each of them knows that their work is bearing fruit, and the Ready for Real Flights helicopter will become an important element of military power. These tests provide not only an adrenaline rush, but also pride in the technologies that bring it to life. Ready to dive into a world where science meets brute force, and unremarkable gray stones are transformed into the most crucial ingredients for creating modern civilization? Forget about the delicate manufacturing of microchips. We're heading into the very heart of metallurgy, to a real devil's kitchen where ferroalloys are born. This isn't just casting, it's the taming of the Earth's depths, the roar of thousands of volts, and the creation of the very vitamins, without which any steel would be just a boring and weak piece of iron. This is the story of how ordinary ore is turned into concentrated power, capable of making a bridge unbreakable and a turbine eternal. Steel is the foundation of everything. Skyscrapers, ships, cars, even the fork you eat with. But steel on its own, obtained simply from iron ore, is a rather capricious lady. It contains a bunch of unwanted impurities, primarily oxygen, which makes it brittle. And it also lacks character. To give it superpowers, incredible strength, resistance to rust, the ability to withstand hellish temperatures, special ingredients must be added. And this is where our heroes come on stage: ferroalloys. These are, in essence, concentrated cocktails of iron and one or more other elements: manganese, silicon, chromium, vanadium, titanium, and many others. They are like the special forces in the world of metallurgy. First, they act as deoxidizers. Entering liquid steel, they greedily snatch all the excess oxygen from it, purifying it. Second, they act as alloying elements, meaning they dissolve in the steel and permanently change its crystal structure, endowing it with those very desired properties. Ferrochrome makes steel stainless. Ferromanganese makes it strong and wear-resistant, and ferrosilicon helps in purification and improves its magnetic properties. So how are these magical powders created? The process begins with gathering the ingredients for our infernal pie. The main component is, of course, the ore containing the element we need. This could be manganese ore, chromite ores, or ordinary quartzite, which is a source of silicon. The second key ingredient is a reducing agent. Most often, this is coke, coal, or charcoal. Its job is to steal the oxygen from the ore. And the third component is a flux, for example, limestone or dolomite, which helps to gather all the unwanted impurities into a separate, easily separable mass. All this is crushed, mixed in strictly defined proportions, and prepared for shipment to the very heart of production. The process begins with gathering the ingredients for our infernal pie. And this isn't a trip to the supermarket, but a real industrial war with the Earth's crust. The main component is, of course, ore. For the black veins of manganese ore, miners descend into deep, dark labyrinths underground, where the roar of drilling rigs echoes in the eternal night. Chromite ores are mined in similar conditions, or in gigantic quarries that resemble scars on the body of the planet. And ordinary quartzite, the source of silicon, is often mined in quarries where powerful explosions lift thousands of tons of sparkling, sugar-like rock into the air. The second key ingredient is a reducing agent. Most often, this is coke, which is obtained from coal. And coal mining is a spectacle of power. Giant excavators remove entire layers of earth to get to the black as tar deposits, the concentrated sunlight of ancient forests. And the third component is a flux, for example, limestone or dolomite. It is mined in huge, blindingly white quarries that resemble giant amphitheaters. Giant dump trucks, whose wheels are taller than a person, crawl along the terraces, hauling out tons of rock. And the heart of it all is the submerged arc furnace. This is not just a furnace, it's a real monster that hums and roars. A huge cylindrical steel bowl, lined on the inside with a thick layer of refractory brick. And now the most important part. 3 giant carbon electrodes are lowered into this bowl from above. These are not the electrodes in your battery. Each of them can be the size of a telegraph pole and weigh several tons. The prepared mixture of ore, coke, and flux, called the charge, is continuously fed into the furnace, completely submerging the ends of these electrodes. Hence the name submerged arc furnace. A colossal electric voltage is applied to the electrodes. But unlike a steel-making furnace, here the arc does not burn openly. The electric current passes through the charge itself, which resists it, and from this heats up to incredible temperatures, over 3,600 degrees Fahrenheit. Inside this white-hot cauldron, a real chemical battle begins. The coke, heated to the limit, becomes extremely aggressive. It starts to tear away oxygen atoms from the metal oxides contained in the ore. A reduction reaction occurs. For example, manganese oxide plus carbon equals liquid manganese and carbon monoxide. This newly liberated, pure, and very hot metal immediately mixes with the iron, which is also present in the charge, forming that very ferroalloy. All this time, the flux is not idle either. It reacts with the gangue and other impurities, forming a lighter liquid layer, slag, which floats on the surface of the molten metal, protecting it from oxidation. When enough liquid product has accumulated in the furnace, it's time for tapping, the most spectacular moment. A worker, using a special tool, or even a small directed explosion, pierces a hole in the lower part of the furnace, called a tap hole. From there, with a deafening roar and a fountain of dazzling sparks, a stream of white-hot metal erupts. This fiery waterfall is directed into a huge ladle. Since the slag is lighter, it flows out next and is poured into another ladle or a special slag pot. Next, the liquid ferroalloy is poured into large, flat molds, similar to giant frying pans, made of cast iron or lined with sand. After the fiery river of ferroalloy has filled the cast iron molds, a period of deceptive calm begins. The liquid metal cools and solidifies, turning into huge heavy plates or cakes. This is not the quiet, peaceful cooling of a pie on a windowsill. The rapidly cooling surface of the plate is covered with a bizarre network of crystalline patterns, and from the inside, a powerful heat continues to emanate for a long time, distorting the air above it. From time to time, a sharp, gunshot-like crack is heard. These are the internal stresses that arise during crystallization finding their release. Each such cake is a monolithic piece of metal weighing several tons, concentrated power, frozen in its primordial form. But this is not the final product. It's just a semi-finished product. In this form, the ferroalloy is completely inconvenient for use in steel mills. Imagine a chef who needs to add exactly 5 grams of spices to a recipe, but all he has is a 5-kilogram stone block of those spices. It's the same for a metallurgist. He needs to add a precisely measured amount of manganese or silicon to a ladle of liquid steel to achieve the desired properties. It is impossible to chip off a piece by eye from a multi-ton plate. A product is needed that can be accurately weighed and evenly distributed in the melt. Therefore, these solidified plates are sent to the final, most brutal stage, crushing. The plates are lifted into the air by powerful cranes and fed into the maw of a real mechanical monster, a jaw crusher. This is a machine that inspires awe. 2 massive grooved steel plates, or jaws, form a V-shaped space. One of them is stationary, while the other makes slow but relentless movements, like the jaw of a prehistoric monster. When a metal cake falls into this maw, a deafening crushing grind is heard, from which the ground vibrates. With a colossal force, measured in hundreds of tons, the steel fangs bite into the ferroalloy. The first crack, then another, and now the monolithic plate is breaking into large blocks, which fall deeper under their own weight, where the jaws come even closer, again and again breaking them into smaller and smaller pieces. But that's not all. The stream of crushed metal is poured onto a conveyor and heads to the next stage, sorting. It falls onto giant vibrating screens, multi-tiered sieves that continuously shake and rattle. This is a real metal waterfall, where pieces of ferroalloy dance and bounce to the accompaniment of a deafening roar. On the top tier, the largest pieces remain, which are often sent back for recrushing. Smaller pieces fall through to the lower tiers with finer openings. Thus, the entire stream is divided into clearly defined size groups, or fractions, from large, fist-sized pieces to small, gravel-like ones. This separation is extremely important, as different steel-making processes require different sizes of ferroalloy for optimal dissolution in liquid steel. And here it is, the final result, unremarkable in appearance, gray, silvery, or black stones of various sizes. They look like ordinary construction debris, but in fact, each such stone is a concentrated code of strength, a chemical key to creating outstanding materials. Each of them is a carrier of the energy spent on its extraction and smelting. In this form, they are poured into huge, strong bags, so-called big bags, marked and sent to metallurgical plants around the world. And there, added at the right moment into a boiling cauldron of liquid steel, they will fulfill their main mission. They will undergo their final baptism by fire, dissolve without a trace, and forever transform ordinary iron into an outstanding material, capable of becoming the foundation for a skyscraper that pierces the clouds, or a reliable bridge that connects continents. Imagine this. Every year, the world produces over 100,000 tons of titanium, a metal that has become a true symbol of innovation and strength in aviation, space, and energy. It's from this metal that the story of creating ultralight and super strong alloys begins, used for manufacturing the most critical parts of airplanes, rockets, and even geothermal equipment. In America, where titanium production technologies have reached the highest level, this metal has become indispensable in creating the future, combining lightness with extraordinary strength. Next, I'll tell you how titanium is born, from raw material to a high-tech material that is changing the world. The history of titanium production begins at the end of the 18th century, when in 1791, a British clergyman and amateur mineralogist, William Gregor, discovered a new metal in the mineral ilmenite, which is now the main source of titanium. Initially, this metal was called menaconite, but later, in 1795, the German chemist Martin Klaproth rediscovered the element in the mineral rutile and named it titanium, in honor of the mythical Titans, giants of ancient Greek mythology. However, pure metal was first successfully obtained only in 1825 by the Swedish chemist Berzelius, although at that time it was contaminated with impurities and practically unsuitable for industrial use. The first attempts at industrial production of titanium began only in the 20th century. In 1910, the American chemist Matthew Hunter obtained a small amount of pure titanium, and a real breakthrough occurred in 1925 when Dutch scientists Van Arkel and de Boer developed a method for obtaining high-purity titanium, which opened the way for its widespread application. From the mid-20th century, titanium production developed intensively, especially in the United States, where the metal became indispensable in aviation, the space industry, and the military industry. The production of titanium begins with the extraction of titanium-bearing raw materials, mainly the minerals ilmenite and rutile, which contain titanium oxides. These ores are found in the form of placer or primary deposits and are widely distributed throughout the world, particularly in Australia, Canada, China, Norway, and South Africa. After extraction, the ore undergoes complex multi-stage processing. First, it is enriched, separating the titanium minerals from the gangue, obtaining ilmenite or rutile concentrates. Then, the concentrates are subjected to chlorination, which results in the formation of titanium tetrachloride, a volatile substance that is purified by distillation. This process allows for the removal of impurities and the production of a high-purity intermediate product. Next, titanium tetrachloride is reduced with magnesium or sodium in special reactors at a high temperature in an inert atmosphere, producing spongy titanium, a porous metal powder. This spongy titanium is then subjected to pressing, melting, and casting to obtain ingots or blanks for further processing. The production of titanium is energy-intensive and expensive due to the complexity of technological processes and the need to work in high-purity conditions. The main industrial method for obtaining titanium is the Kroll process, which remains the standard in the world. It includes chlorination of titanium ore, purification of titanium tetrachloride, and its reduction with a metal, which makes it possible to obtain high-quality metal for aviation, space technology, medicine, and other industries. Thus, the production of titanium begins with the extraction of ilmenite and rutile, goes through complex chemical reactions and physical processing to transform natural minerals into a high-tech metal that combines lightness, strength, and corrosion resistance. The initial stages of titanium production are based on a complex multi-stage technological process that begins with the extraction and preparation of titanium-bearing raw materials, primarily ilmenite and rutile. These minerals contain titanium oxides, which must be converted into chemically pure titanium tetrachloride. For this, concentrates of titanium ores are subjected to chlorination in fluidized bed reactors at a temperature of 1,800 degrees Fahrenheit, where carbon and gaseous chlorine react with the raw material, forming titanium and carbon monoxide. This tetrachloride contains impurities of other metals, which are removed by distillation, obtaining high-purity technical titanium. The next key stage is the reduction of titanium tetrachloride to metallic titanium. The most common industrial method is the Kroll process, in which titanium tetrachloride reacts with magnesium in a vacuum chamber at a high temperature. As a result, spongy titanium is formed, a porous metal powder that contains impurities of magnesium and magnesium chlorides. This reaction mass is subjected to vacuum distillation to remove impurities, after which the spongy titanium is pressed and remelted into solid ingots or slabs. The resulting titanium ingots are then used for the production of alloys, rolled products, sheets, and complex parts. The entire process requires strict control of purity, temperature regimes, and safety, as titanium actively reacts with oxygen and nitrogen when heated. Just look at how incredible it is. A porous, light, and seemingly fluffy mass of metal. This is spongy titanium. It looks nothing like a regular metal bar, but rather like a piece of metal sponge or foam, only made of titanium. But this fluffy material is the first step towards creating strong and reliable titanium ingots, which are then used in aviation, medicine, and other high-tech industries. First of all, titanium ingots can be used to create titanium alloys, mixtures of titanium with other metals that improve its properties. To obtain an alloy, alloying elements are added to molten titanium, most often aluminum, vanadium, molybdenum, iron, or niobium. These impurities change the metal's structure, increase its strength, heat resistance, corrosion resistance, and improve its processability. The production of alloys usually takes place in vacuum arc furnaces, where the metal is melted at high temperatures in a protective atmosphere to avoid oxidation. To achieve a homogeneous composition, the alloy is remelted several times, and after that, it is cooled and prepared for further processing. The next stage is rolling. Ingots or slabs of titanium and titanium alloys are heated to a certain temperature to make the metal more plastic and passed through special rolls. Rolling allows for reducing the thickness of the metal, giving it the required shape and size, as well as improving its structure and mechanical properties. As a result, various types of rolled products are obtained: strips, ribbons, wire, and bars. Rolling can be hot or cold, depending on the requirements for the final product. Sheet metal is made from rolled products, thin, flat blanks that are widely used in construction, aviation, medicine, and other industries. Titanium sheets are characterized by high strength and corrosion resistance, and are also easily subjected to further processing, cutting, bending, and stamping. The production of sheets requires precise control of thickness and surface quality, so after rolling, they are often subjected to additional processing, such as polishing or anodizing. To create complex parts, various methods of processing titanium and titanium alloys are used. These can be mechanical milling, turning, grinding, as well as modern technologies such as additive manufacturing using laser powder bed fusion. Additive technologies allow for the creation of parts with complex geometry that are impossible to produce using traditional methods. This is especially important for the aviation and medical industries, where lightweight, strong, and precise components are needed. In addition, to improve the performance characteristics, titanium products can be subjected to heat treatment, annealing, quenching, or aging. These processes change the internal structure of the metal, improving its strength, hardness, and fatigue resistance. In aviation, titanium is used to make up 15% of the weight of a modern passenger aircraft, which significantly reduces its overall weight and increases fuel efficiency. In the medical field, about 70% of implants, such as artificial joints and dental prostheses, are made from titanium or its alloys due to their biocompatibility and durability.